Welcome to this short presentation on bioremediation, brought to you by Dr. Microlearning in January 2026. Over the next few minutes, we'll explore what bioremediation is, the main techniques used in the field, and practical applications that are helping restore polluted environments around the world. This presentation is divided into three parts: an introduction to the core concepts and principles of bioremediation, an overview of the main types of techniques used in practice, and finally, real-world applications, where these biological approaches make a concrete difference. Let's begin with the basics and why this approach matters. To start, the introduction will ground us in the fundamental ideas behind bioremediation and set the stage for how these biological solutions work in nature and in engineered settings. I'll explain key principles and why relying on living systems can be both effective and sustainable for environmental cleanup. Bioremediation is essentially a biological process where microbes, fungi, or plants are used to degrade or transform pollutants in soil and water. It leverages natural enzymatic pathways to convert toxic compounds into harmless byproducts like carbon dioxide and water, and aims to restore ecological balance without heavy chemical interventions. One of the main strengths of bioremediation is cost-effectiveness compared with mechanical or chemical cleanup, especially for large sites, and it's generally more sustainable because it minimizes secondary pollution. The illustration on this slide highlights how contaminants are broken down and how ecosystems can recover over time, showing the broad applicability of these methods. Bioremediation also has limitations and challenges that we need to keep in mind. The process can be slow, making it less suitable for urgent cleanup, and its success depends heavily on local conditions like temperature, pH, and nutrient availability. In some cases, incomplete degradation can leave residual byproducts that require further monitoring and management. Now we'll move into the second section, focusing on the different types of bioremediation techniques. I'll walk through on-site and off-site methods, as well as plant-based approaches, explaining where each method works best and the trade-offs involved, so you can see how practitioners choose the right tool for the job. In situ bioremediation treats contamination directly at the site without excavation, which cuts transport and disposal costs and reduces ecosystem disruption. It's a gentle, cost-effective option, but works best where soil, permeability, and contamination depth are suitable, and it can be limited by site-specific conditions that slow the process. Ex situ bioremediation involves removing contaminated soil or water and treating it under controlled conditions, which can speed up cleanup by optimizing temperature and nutrients. While this approach improves efficiency, it requires safe handling of treated waste and logistics for excavation, transport, and eventual disposal of residual materials. Phytoremediation uses plants to absorb, stabilize, or even degrade contaminants, making it a natural and visually pleasing option that can remove heavy metals and improve soil health. It's ideal for shallow contamination and can transform polluted areas into green spaces, though it's generally limited when pollutants lie deep below the root zone. Next, we'll explore applications of bioremediation and how these techniques are deployed in real-world scenarios, from land to sea and industrial sites. The upcoming slides highlight common use cases and show how methods are adapted to meet specific cleanup goals and environmental constraints. For soil and groundwater cleanup, bioremediation relies on microorganisms to break down pesticides, hydrocarbons, and heavy metals, often enhanced by adding nutrients or oxygen to speed up microbial activity. The result can be a safe restoration of environmental quality without introducing harsh chemicals, supporting long-term ecosystem recovery. In the case of oil spills, specialized bacteria and fungi can degrade hydrocarbon components, offering an eco-friendly complement or alternative to chemical dispersants. This natural process supports healthier ecosystems during recovery, and specially adapted microbial cultures can be applied in offshore settings for more targeted cleanup efforts. Industrial waste sites benefit from bioremediation through the reduction of toxic pollutants, targeted removal of heavy metals like cadmium or lead, and restoration of soil structure and fertility. The images on this slide show both field cleanup activities and plant-based treatments, illustrating how biological methods can help rehabilitate contaminated industrial lands. Thank you for watching this overview of bioremediation. I hope the presentation gave you a clear sense of principles, techniques, and practical uses. If you'd like to dive deeper into any of these topics or see case studies, I'm happy to continue the conversation or provide additional resources.